Hello and welcome to another video. In this video we're going to be working on number of 1 bits, and in the problem you are asked to write a function that takes a binary representation of an unsigned integer and returns a number of 1 bits. So you're given an integer and you want to return the number of 1 bits, and note that in some languages there is no unsigned integer type. In this case the input will be given as a signed integer. It should not affect the implementation. So basically you're given an integer, and really you're actually just given a normal integer even though they write it like this. And you are basically asked to get the number of 1 bits in the integer. So like here it'd be 3, here it'd be 1, and here it'd be 31. And the way to do this pretty standard problem is whatever our integer is. So let's say our integer is like a bunch of zeros and stuff, right? And then let's just say there's like 30, or not 30, whatever, some amount of zeros, right? So we'll just represent it like this. And then we actually have the part that we care about. So let's say it's like this number here. The way to do this is actually really easy. So first you have a result variable. And second, you can't really know how many ones there are in the whole thing, but you can check if the last bit is a 1 or not. And the way to do this is we can use an AND operation. So if we use an AND, the way AND works is 1 and 1 equals 1, 1 and 0 equals 1, 0 and 1 equals 1, and 0 and 0 equals 0. So we can use this AND operation where we can AND our number with a 1. And if you AND it with a 1, then if it's a 1, we'll get 1. And if it's a 0, then we'll get 0, right? Because in order to get, actually, sorry, I wrote this wrong. So this should be 0, this should be 0. So the only way AND will return 1 is if this is a 1, anything else will give us a 0. So we should basically check for the 1 bit, is it a 1, is it not? Then we add to the result if it is, right? So let's say in this case it is. Then once we did that, then what we really have to do is we have to check the next bit. And so there's another operation that's useful for that called a bit shift. So you want to do a bit shift. So there are normally 2 shifts in most languages, and they are an arithmetic shift, and there's also a logical shift. So what an arithmetic shift does is it shifts your whole number to the right. You get rid of the right bit, and then it fills in. So for example, for most languages, the number stays 32 bits. And then what an arithmetic shift does is it will take whatever the last bit on the left is and duplicate it. So if this was a 0, it'll just add a 0. But the problem with this is, let's say our number is this. It's a bunch of 1s here. Then it will take the 1 and add another 1, right? So it'll get rid of this, but then it'll add a 1, and it'll keep adding 1s and keep adding 1s, and so you'll have an infinite loop. So you don't want this arithmetic shift, you want the logical shift. And what a logical shift does is it shifts your whole number to the right, gets rid of the rightmost bit, and then just puts a 0 in the left no matter what. So then, the nice thing about that is we will keep shifting our number, and we can just check while our number is non-zero, let's keep shifting our number. And that, because while our number is non-zero, that means we still have 1 bits. So essentially, while our number is non-zero, let's just AND it with 1 to check for the rightmost bit, and then shift. And we just keep doing this over and over and over and over. So if we have a number like this, let's say, I'll just go through one example like this, and let's say there's a bunch of zeros on the left that I'm not going to draw, so we'll have a result. We'll AND it with 1 here. So if we AND it with 1, we get a 1, and then our result is 1. Now we shift that number. Basically, we're getting rid of this bit and just adding a 0 here. Now we AND that number with 1, so we get 0, so we don't need to add. Then we shift it again by getting rid of this bit, add a 0 here, AND it with 1, then you don't need to add. Then you get rid of this number, you AND this with 1, so you have a 1, then you have 2. And finally, when you get rid of this number, your number will be 0. So essentially, you're taking your number and you're just shifting it to the right every single time, right? And what a right shift does, once again, is you are literally just moving it this way. So this bit goes away, and you just put a 0 on the end. So you're kind of like popping your last bit off and just adding a 0 on the left. And you keep doing that until your number is 0, and that way we can check the number of 1 bits. So pretty straightforward way to do this. So now let's code it up. We have everything we need. So we're going to have a result, and we'll say, while our number is not 0, because our number can be negative, but the negative should work just fine, because negative number, you can still do this AND operation. So while our number is non-zero, then what we want to do is we want to check if the number and 1 is a 1. So we could just say result plus equals n and 1. So if it's a 1, we want to add 1, and if it's a 0, it will just add 0. And if it's a 1, that means we did have that 1 bit. Then we want to shift our number to the right. So we want to do a logical shift, and the way you could do this is like this. You want to shift it by 1 bit, and the shorthand way in Python is this. So we can do this. And then when our number is 0, finally, we can just return the result. And there we go. Now, there is another way of doing it, and I'll just show you really quickly. So you can do this, or because the rightmost bit is a 2 to the 0 power, so really the rightmost bit will be 1 if the number is odd, and it will be 0 if the number is 0. What you can also do is you could do this. You could say this, and mod 2, and that will also check the right bit. And then instead of shifting right, you can just floor divide by 2. So this also works. And then you can return result. So these are the 2 ways you can do it. Either floor divide by 2 or shift, but because this is kind of like a bit manipulation problem, better to learn the bit manipulation, better to learn the shifts. So this also should work. And there we go. And theoretically, they should be exactly the same runtime. So this is just like variance and stuff. Okay. So I think actually bit manipulation is supposed to even be faster. So because like bit shifts are faster than like multiplying and dividing and stuff. So for the time, when you do these bit shifts, it's basically going to be log n, because what you're doing is you're dividing your number by 2 essentially every time. So for a 32-bit number, it's going to be it's going to take 32 operations, so it will be log base 2 of the number. So this is a log n operation, but because the number is kind of small, it's considered O of 1 because you only have a 32-bit like constant number. You're never going to have like a, million-bit number or something. But theoretically, as your number grows, this operation would actually technically probably be log n, but I'll just write it like this because the numbers are kind of small, right? Okay. And for the space, we're not using anything, so that's just O of 1. Yeah, so pretty easy one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.